Okay, so now that we have looked at some examples of topologies, let's now look at how topologies are related. So let tau and tau prime be two topologies defined on the same underlying set. Which we'll call X. If tau is a subset of tau prime, then we say that the superset tau prime is finer than the subset tau, or equivalently, we say that the subset tau is coarser than the superset tau prime if tau is a proper subset of tau prime. Then we say that tau prime is strictly finer than the subset tau. And if either topologies is a subset of the other, then the two topologies are said to be comparable. Otherwise, the two topologies are incomparable. Okay? So it should be clear at this point that the indiscrete topology is the coarsest topology possible, while the discrete topology is the finest topology possible. So if tau is a topology on a set X, then this topology tau falls somewhere between the indiscrete topology and the discrete topology. And this is the greatest value that we gain in studying the indiscrete and discrete topologies, is that they do provide a spectrum between which any other topology will fall. Now, especially for an uncountable set, the discrete topology has no practical value, nor does the indiscrete topology, except to provide the spectrum. However, in the case of a countable set, The discrete topology does have some applications, especially in discrete mathematics, computer science, in the study of graphs and networks. So even though we will define the discrete topology on an uncountable set, we will gain very little from this. But again, the greatest value of these two topologies is that they do provide a spectrum between which any topology will fall. So recall from the previous lecture that if a given set A is a subset of set B, then the intersection of A and B is the more exclusive set A, that is the smaller set A. So if a topology tau is a subset of a second topology tau prime, both defined on the same underlying set, then the intersection of tau and tau prime is the more exclusive topology tau. Now we can form an equivalent statement using the contrapositive, so equivalently. If the intersection of tau and tau prime is not equal to tau, then tau is not a subset of tau prime. And similarly, if the intersection of tau and tau prime is not tau prime, then tau prime is not a subset of the topology tau. So if the intersection of the two topologies is not one of the two given topologies, then the two topologies are incomparable. So let's look at an example. Let tau sub p be the particular point topology on a given set X, and let tau sub e be the excluded point topology on the same underlying set X. Then the intersection of the particular point topology with the excluded point topology is the intersection of the union of the set which contains the empty set with all subsets of the set X that contain the point P, and we intersect this with the union of the set which contains the entire set with all subsets of the set X that do not contain the point P. Notice that the only two sets that these two topologies have in common are the empty set and the entire set. That is, the intersection of the two topologies is the indiscrete topology, but as the intersection is not one of the two given topologies, we have that the particular point topology and the excluded point topology are incomparable. Okay? So we'll look at another example. let the set X be a two-point set containing the points A and B, and let the point A be the specified point, the indiscrete topology on X is tau sub I, and this is the set containing the empty set and the entire set, which is the two-point set. The discrete topology on the set X is tau sub D, and this is the set containing the empty set, the singleton set containing A, the singleton set containing B, and the two-point set, that is the entire set. The particular point topology on the set X is tau sub P, and this is the set containing the empty set, the singleton set containing the point A, and the entire set. And the excluded point topology on the set X is tau sub E, and this is the set containing the empty set, the singleton set containing the point B, and the entire set containing A and B. So notice that the particular point topology is strictly finer than the indiscrete topology and is strictly coarser than the discrete topology. And the same is true of the excluded point topology. The excluded point topology is strictly finer than the indiscrete topology and is strictly coarser than the discrete topology. And as we have already demonstrated in general, the particular point topology and the excluded point topology are incomparable. So if the set is a singleton set, and we'll call that the singleton set containing the point A, then the indiscrete topology on the singleton set is the set consisting of the empty set and the entire set, which is the singleton set containing the point A. And the discrete topology is the set containing the empty set, and once again, the entire set, which is the singleton set containing the point A. And hence, the indiscrete topology is equal to the discrete topology. So, in the case of the underlying set being a singleton set, we have that any topology defined on a singleton set is indistinguishable from the indiscrete topology. So now we can define a new type of space, A topological space consisting of a 2-point set and either the particular point topology or the excluded point topology, is called a Sierpinski space. Now, this name is in honor of a Polish mathematician. I am not a Polish speaker, so I may have butchered this name. So if there are some Polish speakers out there that know the correct pronunciation, please let me know. Until then, I pronounce it Sierpinski. And again, a Sierpinski space is a 2-point set on which is defined either the particular point topology or the excluded point topology. And as we saw in the previous example, for a 2-point set, the particular point topology is strictly finer than the indiscrete topology and strictly coarser than the discrete topology. And the same is true of the excluded point topology. And so, a Sierpinski space is the smallest topological space that is neither indiscrete nor discrete. And we'll have more to say on Sierpinski spaces a little later. Okay, so next I'm going to introduce the concepts of open and closed sets. Now, this is where beginning topology students tend to become the most confused, and this is because in our previous experience with the real number system, we are introduced to these terms out of context. So let X together with some topology tau be a topological space. A subset U of X is open in the space X if that set U is in the topology. So in other words, we call the sets in the topology open sets. So once again, let X together with some topology tau be a topological space. A subset A is closed in the space X if its complement is in the topology. That is, the set A is closed if its complement is open. So notice that the terms open and closed have no meaning outside of a topological space, and that within a topological space, the complement of an open set is a closed set, and the complement of a closed set is an open set. Now, let the underlying set be the real line. The subset of the real line containing those real numbers strictly greater than 0 and strictly less than the number 1, we usually indicate this way using parentheses, and we call this an open interval. So the subset of the real line is called an open interval because there exists a topology on the real line, which we call the standard topology, such that this subset, is in the topology. So again, we first encountered this term out of context. We first learned that this interval is called an open interval without realizing or without being told that the reason it's called an open interval is because there exists a topology on the real line called the standard topology, for which this set is in the topology.